Hi guys. Okay, in this video we're going to tackle Einstein's special theory of relativity. Einstein's special theory of relativity. And this here theory, it's a theory that Einstein devised and published in 1905. He finished devising it, or you could say he published it in the year 1905, which is known as the Year of Miracles. In this paper that he published, he published four papers, I believe, maybe about four or five. He published special theory of relativity, the photoelectric effect. Let's see, I think he published E equals mc squared, and he published a derivation or a proof that atoms exist by Brownian motion. Uh, and yeah, that's Einstein. So that's a little bit about Einstein. Just wrapping it up, what I just said. He proved atoms exist. He proved light exists as a particle. He proved, relativity exists. Relativistic motion. He proved relativistic motion exists, and then he proved that energy and matter are the same thing. All in the year 1905, he published his findings on this. And then later we found that in later years he actually got the Nobel Prize. That's a big accomplishment, a big achievement to have. Every day, me or you, we don't have Nobel Prizes. Whereas our Nobel Prizes, we're not going to get one because we're not Albert Einstein. But yeah, Albert Einstein. So that's a little bit about the year 1905. But special theory of relativity. Special theory of relativity. This right here is just a theory of space and time, and it's based on relative motion. So let's start out. Let's start out by saying, let's say we have the first principle of special relativity, and we have the second principle of special relativity. These are just two axioms or assumptions that Einstein made. There's two sort of statements that he just took and said, okay, if I'm gonna hold them true, I'm gonna assume them to be true, and then I'm gonna try and derive a theory to explain reality as a fundamental basic framework of what's going on with reality. So the first principle is this. It is the laws of physics are the same for all non-accelerating systems. And the second principle is this. It says, let me actually clear this to make some room. Second principle is the speed of light in a vacuum must always be measured to be the same for all non-accelerating systems. So what do these two principles mean? What are these two assumptions? What are they? What are they saying? Well, what they actually are saying is, Einstein's saying it's an establishment of relative motion. It's an establishment of relative motion. So if you think about Newton, Isaac Newton, and the people before Albert Einstein, maybe not Galileo. Galileo might have been sort of the same sort of thinking as Einstein, but Newton and regular classical physics, they said there is an absolute background space and time, and that everything that's moving, moves relative to this background space. They follow the laws of physics. They're all the same. The laws of physics are the same for all moving things, and they exist relative to this background space. They make sense relative to this background space. Einstein said that's not quite the idea. Einstein says, hey, if you want to consider things to be moving, you got to consider them moving relative to other things that aren't accelerating. And we hold the other things to be at rest. How do we know that? Well, we have evidence, we have indirect evidence, but we're going to assume that to be true first. To understand more deeply what these two principles mean, the second principle states it states this: the speed of light is always measured to be the same for all non-accelerating systems. All that is saying is it's defining what a rest system is. It's the definition for what it means to be at rest. If you measure the speed of light to always be the same, then you are considered to be at rest. So let's say we have a box right here. Let me backspace that. Let's say we have. Let's say we have. Let's say we have Jimmy here, and let's just call him Jim. 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 Hey, Jim. So, Jim. Let's say he's moving forward, right? He's on Earth. He's walking on Earth. Here's Earth. He's walking. Let's say here's a lamppost. And here's also another lamppost. And he's walking this way. Let's say light's going this way and light's going this way. What that second principle is saying is it's saying, hey, he's not accelerating. Therefore, he's going to always measure the speed of light to be the same. And if he's measuring the speed of light to be the same, that just means he's at rest. That's all that means. He can be considered to be at rest. Now, technically, it's also true that the Earth is at rest and he's moving. You can switch between each one of these, according to Einstein. You can say this: if you're not accelerating, or if you're measuring the speed of light to be the same, you're considered to be at rest. That's ways you can look at it. If you measure the speed of light to be the same, then you're always going to be at rest. Whether you're moving towards the light, or the source of the light right here is moving towards you, it's always measured to be the same. Always. And the first principle is basically saying everything that is at rest, if you're at rest, let's say you're at rest, you're measuring the speed of light to be the same. Here's Jim again. All these things that measure the speed of light to be the same, they all share the same laws of physics. It's just saying, hey, what laws of physics do these things have? It's the same laws of physics that all of them have. And they exist relative. They exist relative to these things at rest. They're a consequent of these things being at rest. So right there, that's just an establishment of relative motion. That's all that is. It's just an establishment of relative motion. It's establishing, it's saying, hey, there's relative motion. The first two principles saying there's relative motion. And from there, we derive a whole theory of space and time. Derive a whole theory of space and time. How? This is how. So let's say we have a laser right here, right? Let's say we have a laser. Change the color. And let's say it's a red laser. Here's a light beam. Let's say it goes to the ceiling right here. Let's say this is at rest. Let's say this laser light's at rest. And it's shining its light straight upwards. Or we can have the laser like this. Let's say we have our laser like this. So we have our laser pointed in this direction. Or maybe let's say we even have our laser, let's say, pointed in this direction. Any direction, whether the light's going this way, that way, or any direction at all. Let me draw a red beams that just look cool. Red beam. I'm talking about Jim Beam bourbon, talking about laser beams. So anyway, so what Einstein's saying here is, like he says, hey, This laser, let's say we're going to get it, we're going to move it. We're going to get the laser beam, the laser light, the laser flashlight pin. We're going to move it in this direction. Any one of these, we're going to move it in this direction. Because of that, this beam right here must travel a longer distance. Let's draw the red beam right here. In the same period of time that we measure, let's say this light beam to travel from here to here, in that time, as it takes this beam right here to go from here to here, or whatever distance it does in that time, it's a longer distance for all of these pins right here. It's always a longer distance. No matter which way you look at it, it's always a longer distance. But remember the second principle, it says this. It says c, which is just the speed of light in a vacuum, is always constant. It must always be measured to be the same. So if you look at the speed of light, it's a d over t. If d increases by some factor gamma, then t, the elapsed time, must also be increased by some factor gamma. So in short, light whenever some source of light is moving, if it's actually moving, and we're going to keep it simple here, it's not accelerating. If it's moving, its light must travel longer distances. Therefore, the elapsed time for the laser pin or whatever the source is, for it to always measure the speed of light to be the same, its elapsed time must also increase. It must also increase in order for this, let's say, this gamma here and this gamma to cancel, and this here stays the same as c. It's always measured to be the same. So what do we call this? We call that time dilation. That's what Einstein, I believe, called it. I'm not sure if he coined it that. I'm sure he did. I'm sure he coined it time dilation. But that's time dilation. Another way to think of it, let's say we have, let's say somebody who's at rest. Not too red, looks like blood. Make it look like blood. Let's try. Blue looks good. It's like a science color. Okay, so we have this timeline for this person at rest, and we have this timeline for this person who's moving relative to the person who's at rest. So it's just a dilated time. It's stretched out. It's enlarged. So let's say from here is 0 to 5 seconds. This is 0 to 5 seconds. Let's say this is maybe 3 seconds. So for example, for the person who's moving, might experience 3 seconds, while the person at rest experiences 5 seconds. And that's time dilation. That's kind of a way you can look at it. So yeah, the faster you move, the quicker your time's going to be. And you can switch this role. You can switch that role. And it actually, I said the quicker it's going to be. That's not correct. In fact, it's not even correct to say your time slow down. That's not correct. That's not the way to look at it. It's to look at it as your time being dilated. It's stretched out. It's not being slowed down. If it was slowed down, it would look more like this. It would be, let's say, eraser. Remember Einstein, or it's originally called time dilation. If it was slowed down, then these two timelines, elapsed times, would be the same, 0 to 5. And the rate at which, let's say maybe a point in this time, let's do pink, it's going this way at some rate, and this point it's going at this rate at a slower rate. That's not the right way to look at it. According to Einstein, speed of causality is the same. The speed of light's the same. Speed of causality is the same. Causality stays the same, the speed of it. These speeds should just stay the same. It's just times lines that dilate or stretch out. And you can switch those rules. Remember, if you're not accelerating, you can always measure the speed of light to be the same. So remember the laser light right here, like that, and this laser light was moving, and this time got dilated. Well, at the same time, from this point of view, this can be at rest, and now this time dilation, this time is being dilated, and this is moving. But remember that you can switch between things being at rest and not being at rest. Either way, that's the right way to look at it, according to Einstein. Uh, and another reason why I know, according to Einstein, how it is dilation and it's not slowing down. If you look at the time dilation formula, I believe it's something like this: T prime is equal to T. I think it's going to be times gamma. So what we have here is we have T prime is equal to the original elapsed time dilated. It's multiplied by some factor. It's enlarged or stretched out. It's not slowed down. It's not the right way to look at it. And yes, this is the time dilation formula. Gamma, in this case, is the relativistic adjustment factor. Gamma is equal to 1 over the square root of 1 minus b squared over c squared. So let's say whatever speed you have, you plug it into here, and then you solve for the number it is. Maybe it's 90.9 or 0.8 or whatever it is. Depending on your speed, the higher your speed is, the more greater your time can be dilated. And the slower your speed is, let's say if it's 0. If it's 0, this just goes to 0. The v0, this goes to 0, and this just can be 1 minus 0. The square root of 1 be 1. Be 1 over 1. So the elapsed time will be the same if you're not even moving at all. But if you are on the speed of light, then you can imagine that this is going to just be 1 over square root of 1 minus 1, or 1 over 0. In one sense, that's basically saying that gamma is infinity. And basically, your elapsed time, your dilated time is infinite. Infinite. Which all that means is if you go at the speed of light, you don't experience time. You get from place to place instantaneously. If you can actually reach that speed. There's refraction, there's particles, there's no such perfect vacuum, so light's always bouncing and hitting things. It slows down. It's not exactly going at the speed of light. But technically speaking, it pretty much essentially gets from place to place instantaneously because it doesn't experience time. Okay. Now, by the way, 2 more notes I wanted to say that I didn't say before. For one, that first principle is basically saying if you have a constant velocity, then that's just saying, by definition, constant velocity is just to say, you share the same laws of physics as every other thing that has the same laws of physics as you. If you're sharing the same laws of physics with anything else at all, or most things at all, or multiple, many numerous things, then you have a constant velocity. If you have the same laws of physics as something else, you have a constant velocity. Things that are accelerating do not share the same laws of physics. Let's say, I don't want to get too deep into that, but you could imagine, laws of physics being different for things that are accelerating. It's a little bit different in that case. But the second point I want to say is, maybe it's a little confusing. You're saying, how can I be at rest while the other thing is not at rest, but the other thing's at rest and I'm not at rest? Well, I actually don't think scientists do have a complete answer to this. My best answer that I've gotten from my physics book, whenever they was referring to sort of a contradiction in maybe quantum physics, they pointed out a good analogy that I want to use for special relativity. And they said, it's something like, this is not like saying somebody is short and tall at the same time. But it's more like saying somebody is short and fat at the same time. 2 different things going on there. Not completely contradictory. Anyway, let's go into length contraction. Length contraction. So for one, let's say we have this laser right here. Let's see. There's a laser right there. And then we have a laser right here. So we got 2 different lasers. Let's say this one's at rest, and this one has some velocity moving in this direction. So these lasers must always measure the speed of light to be the same. So let's call this speed of light as measured in this system right here, this laser pin, it's going to be C subscript blue. Let me me change that color. I don't like the red there. Let's try. Let's just try yellow. That's going to be C sub blue is equal to C sub red. These two speeds of light must always be measured the same. So we know C sub red, which is this red right here, C sub red is going to be equal to D divided by T. We know T is increased by some gamma factor. So, if we want to measure, if given the T is increased by some gamma factor, we're going to have to say that C sub blue, let's say D divided by T, blue, D must be increased by some gamma factor. And these two things work together. They work together to make speed of light to be measured to be the same, by either one of them. So if you think of, the speed of light being contracted, if you think of length being contracted, this is basically what you're saying. Space literally contracts around this laser right here. It's literally contracting around it. Now you think it is contracting like this. It's not the right way to look at it according to Einstein. So let me backspace all that. According to Einstein, it's really space is contracting more like this. Space is literally contracting to this thing here. So basically, let's say we have a meter stick for this thing right here, relative to this thing. Anywhere in this system's space, it's going to be shorter. It's going to be measured to be shorter. It's a meter stick, and it's measured to be shorter. And you can switch the roles here. This could be considered to be at rest. Its length is contracting. Either way, it's the same thing. So, and another way to look at it, let's say this gamma factor right here, this T is increased by this gamma, which means this D is also increased by the longer distance it travels. And I guess you can say another way of looking at it is maybe we can actually, and actually I put a gamma here. I didn't mean to put a gamma there. I meant to put 1 over gamma. I believe that's what I meant to put. 1 over gamma. Is that right? Let's see. Yeah, because I mean, if its length being contracted, it should be 1 over gamma. So if I put a 1 over gamma there, then I can put a 1 over gamma here. This cancels, and this stays the same, this stays, and now we have a constant speed of light measured in either system. Really, all that's happening is this length is being contracted. That's all that's really going on. And I might have did the math wrong a little bit there, but you get the idea. So yeah, this space is contracting, and anything moving relative to it in its space is contracting. So we're already starting to get the idea of how space and time is. We're understanding how space and time actually is according to Einstein. So from there, we can talk about relativity of simultaneity. I feel like I'm missing something though for a second. What am I thinking that I want to say? Oh yeah, I just also want to say, the payoff that we get from here is that space and time is personal. It's not, we all have our own space and time. It moves at different rates. Things have different sizes relative to us, and we have our own personal time. And it's Einstein right there. Time and space is personal, and you can be considered at rest while really you're not at rest, and it's craziness. But let's talk about relativity of simultaneity. So we're getting a little bit deeper into Einstein's special theory of relativity. So let's see. Let me clear this. So let's say we have a guy on a go-kart. We have Jim on a go-kart. Here's Jim. going to the go-kart. Let's say here's let's say here's let's say here's Kim. Here's Kim, and she's over here at rest. She measures the speed of light to be the same, no matter how she is. And here is the Jim moving forward like this. Uh, and then there's a lamp post right here. There's a lamp post right here. So as Jim rides on his go-kart, on the road somewhere, maybe in Kentucky or something, I don't know. He's going to be traveling this way, and they're going to have light coming from this post reaching his eyes, and light coming from this post reaching his eyes. And Kim right here, she's always she's gonna see the light from this post and the light from this post from her eyes. It's gonna reach Jim at the same time because the speed of light's always measured to be the same. And let's just say Jim is right in the middle. Let's say he's right in the middle of these two posts relative to Kim. So he's gonna see these two light beams, these light signals reach Jim at the same time. Okay? But Jim is moving forward. So technically speaking, he should see this light right here reach him first. He should see that light reach him first because, it's like he's moving relative to Kim. So he's actually coming towards it. And technically the distance is shorter, I guess you can say. That's pretty much what it's saying. But if you remember the first two principles, Jim is at rest. Jim is at rest. So how is he seeing these two light things, these light signals reach him at the same time? Well, according to Einstein, the problem here is that they're simply not measured to be the same. They're not really. The two things are out of sync. Two events is measured from two different people, whether they're moving or not. Whether they're moving really is the key thing. They're out of sync. You don't measure them to be at the same time. They're not happening at the same time. It's not simultaneous. It's not simultaneous events from either system's point of view. They're out of sync. So from her point of view, he's moving forward, and the light should reach him first, and the light from the back should reach him after. If you think about it, let's say here's the speed of the go-kart V. If you add, we're going to say minus C. That's going to be the speed of light relative to Jim. V minus C is the speed of light relative to Jim as he's moving as relative to Kim. And that's from this post. And from this post it's going to be V plus C. I might have had that mixed up. It's actually, that's mixed up. For this post it's going to be V plus C. For this post it's going to be V minus C. From there, then you would say, hey, this light from this post should reach Jim first, and this light right here should reach him after. Really, it's just the different speeds of light. That's really what it is. But the speed of light must measure to be the same. And Jim is actually at rest. So, actually what's going on is, since this light's reaching him first, and this light's reaching him after, and Jim's really at rest. They're not moving at different speeds. What's going on is that they're actually not happening at the same time as Kim's measured them to happen. They're out of sync. They're not simultaneous. So, really just trying to understand space and time here. Basically, an understanding of time according to Einstein, this might not be the best analogy, but let's say, whenever you're in Kentucky or Albuquerque, what's going on with coronavirus, and Joe Biden maybe in Washington, D.C., it's not going to be, the same thing that's happening to somebody who's flying in a rocket in the International Space Station or a jet. It's two different things going on. You just can't say, that might not be the best analogy. It might not even be true or valid. But you get the idea, getting an understanding of time. We're comprehending time according to Einstein. Different from Newton and the people beforehand. If you're moving, you measure two events to be out of sync with somebody who's at rest. And actually, this effect becomes more dramatic, more forward and more backward. More in front and more behind. effect becomes more dramatic. And they call that relativity or simultaneity. And I gave a little sloppy explanation beforehand. I didn't think completely through. But luckily, I've thought it correctly through as I worked through. Not perfect. It's a problem whenever you get, when math and science you have problems. You can't always think of everything completely through right beforehand. If that was the case, it wouldn't be a problem. You can't just figure it out all the way from the beginning. You got to work through it and try new things, and that's how we solve problems. And sometimes you can pretty much solve it from the beginning if it's an easy problem, but when you're dealing with hard problems like I do often, you're going to deal with stuff like that. This is definitely Einstein we're talking about. It's a little complicated. I'm no expert. I'm just an amateur. Anyway, let's delve a little bit deeper into this. Maybe, if I don't cut it short, if the video stops, it's because I gave a very poor explanation of what I'm about to talk about next. And you can just ignore it. If not, we're about to move forward and we're about to try and understand E equals mc squared. The most famous equation in the whole world. E equals mc squared. Now, this whole video doesn't really revolve around too much math. It's just giving the insights of the concepts of special relativity and their phenomena. We're not really deriving too much with math. And really, to be honest, the math is not that hard. It's just a little bit of Pythagorean theorem, and geometry, and some basic algebra. And you can really just derive all of special relativity. That's the most basic level, maybe in a common modern physics course. Anyway, let's get into E equals mc squared. This is the relativistic energy. That's what they call that. Now, if you think of relativistic mass, from what I'm understanding by I've read from my books and what I've heard, I believe, there is no such thing as relativistic mass. It's relativistic energy we're talking about. There's rest mass. There's rest mass. And actually, the true equation for E equals mc squared is more like this. It's going to be gamma times m sub 0 v squared. This is the true equation. And that's if you're moving. Remember gamma, it's going to be 1 over square root of 1 minus v squared over c squared. That's gamma. And basically all that's saying is as you increase your speed, your energy increases. You multiply it by your rest mass. The mass that you have whenever you measure your speed light's always the same. But so from here, let's try and understand E equals mc squared. And E